Hi guys, I'm Willa Vaughn.
Hi, I'm Anna Jones.
Christopher Crow at your service, and we are coming at you guys with our Math for Teachers 2 final, where we're going to go over a little bit of every single module we've done so far. So without wasting any time, let's jump right into it.
Okay, so Chris, how do we know what graphs to make for each scenario?
That is a good question, Willa. So for some context, this is question 1, module 1, where we had to create graphs for specific scenarios and explain how the graphs related to the scenarios. So in the one you're about to see, is it going to represent a car traveling X amount of miles while using up gas? Here we see the star is going to represent the car. We have distance in miles as the x-axis, and then gallons of gas at the y-axis. So as the star travels a certain distance, we see that the miles increases, but the gallons of gas decreases. And then you see the straight line on the graph, which represents the car stopping to fill up the gas. So the gallons of gas increases while the distance is unmoving because they're not going anywhere. And then finally, when they stop filling up and start moving again, the distance in miles will increase as the gallons of gas slowly decreases.
Okay.
Yeah, I can see that.
And our second example is going to represent an elevator stopping at every floor until it reaches the top to either pick people up or let them off. So here we see that the little block on the graph is going to represent the elevator, and it's going to go up, it's going to stop for a minute, let people on or off, it's going to go up, stop for a minute, and then do that all the way up to the top. And that makes sense because when an elevator is stopped, it's not moving. It's simply letting people on or off, which, drags a certain amount of time, and then it will go up, stop, and so on and so forth.
Yeah, I like it because the elevator is basically a bunch of stairs.
Yeah.
That is very accurate.
I like
It's
that. I like the
definitely
visual for that.
Oh yes, it's very well put together, if I say so
Oh yeah.
myself.
Well, thank you, Chris.
You are most welcome.
All right, well, I have a question for you.
Yes, ma'am.
So, where exactly does g of x come from?
Okay. Glad you asked this question. I like to answer it. So for what we're going to use, we're going to actually put this in the question 2 module 1 reference. And I'm going to drag our faces up a little bit so we can see it. All right, so what this is, our g of x comes from the equation g of f of x equals f of x plus 8. So over here we have our little table that shows our x values, which is 0, 1, 2, 3, 2, and 3. And then we have our f of x, which is f of x equals 3x. And then our g of x is f of x plus 8. So what all of that means is that here in our graph, we have our blue line, which is just our x values, and we have it as 0, 1, 2, and 3. And then our orange line represents our f of x equals 3x. So what that means is we're plugging in these numbers, sorry guys, like take our 1 for example, and you're going to plug that into the x. So that's basically going to be 3 times 1. So our orange line is going to triple. And then our gray line is going to be our g of f of x equals f of x plus 8. So that means you're taking your answer from your f of x and plugging it in and then adding 8. So while 3 is down here in the orange, when you plug it in, you're going to add 8 and it's going to be 11. So you're taking the f of x and plugging it in, and that's where you're getting g of x from.
Okay, so f of x is like the x in g of x?
Yeah, basically, yeah.
So it's kind of just plugging in the right numbers and making sure it's calculated correctly.
Yeah, plug and chug. That's what it is.
That's catchy.
Very nice, Willa.
Yeah, I like that rhyming in there. Yeah, helps me remember.
It works well.
Yeah, definitely.
Alrighty. So I actually have another question that I would like to ask Anna.
Okay.
Anna, how exactly do you find the points in order to graph a function?
So for this function, we just kind of took a whole range of numbers. We went from -10 all the way to +10. And that's just our
Okay.
our base x values. Um, and you can see that here as the blue line on our graph. Um, and then we're going to move on to y equals x squared. And y equals x squared is unique because it makes a parabola shape. And you can tell that by our red line here. And then we're going to see our gray line, and that's y equals x squared plus 7. So you see that it's basically just like the red line, but it's been moved up 7 units because of the plus 7 that we put on the end.
Yeah, so that's kind of like the graph from before with mine, where your y is your g of x, so you're just taking your red line and adding 7 to it.
Right. Yeah, it's exactly like that. And then you
Okay.
can see here with our yellow line that it's basically the same, y equals x squared minus 7. So it's going down 7 places.
So just being translated to different spots by adding or subtracting different numbers.
Yes, that's exactly what we're doing, Chris.
I like
And you can tell that the red, gray, and yellow lines are similar because they're all parabolas.
Yeah, they're just a little bit different from each other in
Right.
height.
And the base X line, the blue line, is very different because it's just going straight.
Yeah. Okay, I like that.
Well, that was very well explained, Anna.
You're welcome.
Okay, so Chris,
Hmm.
what is the origin of a graph?
That is another very good question, Willa, and I'd be happy to answer it. So for another reference, this question is going to be answered through using problem 6 on module 1. So through the graph that you're about to see appear, the goal was to find the equation of the line that is tangent to the circle of radius 9 at 0, -9, and whose center is at the origin. Now, that's a lot of words, so let me simplify this. That little yellow square right there represents the origin of the graph. The origin is simply the center point of the graph. It's 0, 0, looking at it in the way of an ordered pair, just the exact center of the graph. And with our little yellow square representing that, we see a pink line drawn across the bottom of the graph along the one point where the circle touches that line, which is 0, -9. Now it's asking to explain the equation of the line. So obviously the radius of the circle is 9. So that's where the tangent is going to be, is at the opposite end of the radius from the origin, 0, -9. And that would be correct for the opposite as well, which is actually part B of question 6, where it's asking you to show off the tangent of the circle at point 0, 9, not 0, -9. And the reason that is the way that it is, they are opposite equations of a line, and they are tangents because they are opposite of each other, but they are still equal because of the same distance, the same spot, just different area.
Okay.
Yeah, that makes a lot of sense.
Yeah, it does.
It should make much more sense once it's been explained and kind of dumbed down, quote unquote.
Okay.
Here, B, you'll see the example of the equation of the line at point 0, 9. And then part C is going to show off and compare the two graphs and how they are opposite of each other. And the same thing would go for -9, 0, and then 9, 0. They are complete opposites of each other, but because of that, they are equal and therefore tangents.
Okay, yeah, I like how it's laid out right here where you can really see how they're opposite of each other.
Yeah.
Right, thank you, Chris, for that explanation. Helps me understand it
You
a little
are
more.
most welcome. Now,
Mm.
I actually have another question for Miss Anna. Willa's kind of getting left out here, but not for long. Just trust me. And I have another question for Anna, and that is there one concrete formula to use for finding out, let's say, the volume of a whole figure?
No, there is not just one formula to all this. Even though I kind of wish there was, there's not. So here we're going over module 2, question 4. And here we have a cylinder and a cone that both have the base radius of r and the height of 2r. And then we have a sphere that has a radius of r. So we're going to show the ratios of the values of the sphere to the cylinder, or show that they are 1 to 2 to 3 ratio. So first we gotta start finding our volumes. So we're gonna start with the cone. So we can see here that the formula for the cone for volume is V equals 1 over 3 V times H. And V is going to be base, H is going to be height. So we actually need to find the base for this, for the cone. And so B equals pi r squared is going to be the base. So then we're going to get B in the equation, and that's going to look like V equals 2 over 3 pi r cubed. Right? And then we're going to figure out the volume of the cylinder next. So V equals BH, and we already know what BH means, so we got to find the base, and base equals pi r squared. So we're going to plug everything in, so that's going to be 2r times pi r squared, and that's going to give us volume equals 2 pi r cubed. Alright, and then we're going to find the volume of the sphere, which that's relatively simple this time because we don't have to find the base. So that's V equals 4 over 3 pi r cubed. And then we're going to get that all together to find the whole volume of this figure. And that's going to be 2 over 3 pi r cubed to 4 over 3 pi r cubed to 2 pi r cubed. And then we can show that this is in a 1 to 2 to 3 ratio, because if you divide the volume of the cone by 1, it will equal 1. If you divide it by 2, it'll equal 2. And if you divide it by 3, it will equal 3.
Man, I wish there was one formula for all this.
That was a long, detailed explanation.
Yeah, I mean, it was very well
So it is
put.
appreciated in this one.
Yeah.
Yeah.
One
Very
formula.
well
A
explained,
little
and I
bit
do
better way to
appreciate it.
show it, but
Yeah. Well, good job, Anna. Thank you.
you're welcome.
Alrighty. Now Willa gets to ask a question, finally.
Yes. Anna, this question's for you again. I'm sorry.
Oh, that's fine.
How do you find the base for the formula?
So the base is going to be the area of the base. Move on. Bases right here. So for this question, which is module 2, question 5, we have to find the surface area of these two figures. And to do that, we're going to have to find the base. So we're going to answer that question in this question, okay? So for this first figure, figure A, you see all the measurements clearly right there in the figure. So we're just going to go ahead and start with the formula. So SA, being surface area, equals 2B plus pH. All right, so first we're going to find the base. B equals 1/2 AB times H. Or I'm sorry, 1/2 times AB, A plus B times H. and that's going to give us B equals 246 centimeters squared. And it's squared because A plus B, right? And then that's going to be times H. All right, and then we're going to find the perimeter. That's going to be 12 plus 25 plus 16 plus 15. That's everything around the shape. We're not including 2 centimeters here because that is like the width of the shape. We're not going to include that in the perimeter.
Okay.
All right, and then we're going to add it all into this formula again. The SA equals 2B plus PH.
Plug
So
and
it's gonna,
chug,
yes, we're plugging and chugging. Thank you, Willa.
It'll catch on, I
So,
promise.
yes, it should, especially after this.
Yeah.
All right. So surface area equals 2 times 246 centimeters squared plus 68 times 2. All right, and that's going to equal 628 centimeters squared. So that is the surface area for figure A. And then now we're going to do figure B. So it's the same formula for the surface area, SA equals 2B plus PH. So for the base for this one, being that the figure is a little bit different, we find the base a little bit different. It's going to be 1/2 B times H. So the B in this case is going to be the base length, while the base in, or the B in the other one was 2 different lengths. So it's
The base
B
can kind of
equals,
switch around on these figures, can't it, depending on what exactly you're trying to find.
right, the shapes make a big difference.
Yeah.
So this one's B equals 1/2 BH, and then that's going to equal 30 n squared. And then we're going to have to find the perimeter. So that's going to be 5 plus 13 plus 12. And you can tell in this one, we didn't use the 4 meters because it's part of the width, not the perimeter. It doesn't need to be included in the perimeter, I'm sorry.
Okay.
So P equals 30 meters. And so we're going to plug and chug, as Willa puts it. So surface area equals 2B plus pH. That equals 2 times 30 plus 30 times 4. And that's going to equal 180 meters squared.
Okay. It's a lot of math.
Very nice. Very
Yeah,
well
I hope-
explained. I appreciated that, Anna.
I hope that made sense.
It did. I like how you're taking all the formula dense ones from us too. Well appreciated.
Oh, you're welcome.
All right.
All right, Chris, I have a question.
I have an answer.
How can you tell the number of faces on a hedron shape?
That is actually far easier to answer than most people might think. So here we see 3 different shapes, and they are called Schlegel diagrams. The first one is a tetrahedron, the second one is an octahedron, and the final one is an icosahedron. And so what that means, the first figure you see has 3 obvious faces, like a pyramid. It has 1, 2, 3. But tetra means 4. So where's the final face? Well, it's the one underneath the entire figure. It's the bottom of the figure, if you'd like to consider it that, if it makes it easier for you. And for reference, this is question 6, module 2. So that is how you understand that it is a tetrahedron. The third one is octahedron, so of course 8 sides, and there are 7 sides on the top of the figure. You can count them: 1, 2, 3, 4, 5, 6, 7. And of course, where's the 8th figure? Willa, help me out here.
On the bottom.
On the bottom. And the same goes for the icosahedron, which I believe is 20 sides or 20 faces. So count them all. You have 19 all on top, and then the final face is on the very bottom of the figure. They will try and trick you by not showing you all of the faces, and you have to kind of, start freaking out and wondering it is. Don't freak out. It's very simple when broken down.
Also, the thing I like to use to figure these out is I like to use those prefixes on it, the Latin prefixes tetra, octa, and icosa, because those prefixes mean 4, 8, and 20. So you take the math out a little bit of that one, kind of helps you out.
Yeah, but I'm glad you reminded us about that bottom side because I almost forgot about that.
Definitely.
You are most welcome, the both of you.
All right. Oh, oops, guys, sorry.
That's just further proof.
All right, so Chris, another question for you. What is
Another answer.
What is the difference between concave and convex?
That is another very, very good question. So the major difference between concave and convex is one of them is supposed to be talking about a figure that is breaking inwards to a certain extent, and then one of them is breaking outwards. So the one we see here is a concave polygon, whereas some of the ones you saw on the original question slide are convex. So this one is concave because you see at the bottom, towards the pointed area, labeled 3y, those areas are kind of pushed into the shape. They're kind of pushing inwards, whereas a convex shape is going to be pushing outwards to an extent. So you could say that if this were a convex figure, then those broken in areas would actually be pushing outwards instead of inwards like they currently are. And so with that information, the goal is, again, this is question 3, module 2, we have to demonstrate how to find the measures of the angles in the concave polygon. So here we have a measure for each angle, or what? Yes, a measure of some sort for each interior angle of the polygon. So here we're going to use the formula n minus 2 times 180. And in this case, n is going to be the number 8 because there are, count them, 8 different points on this figure. 1, 2, 3, 4, 5, 6, 7, 8. And so with that, we're going to do 8 minus 2 times 180 is 1080. And so we're going to take all of the points within the figure, add them together. That's going to be 1080, more proof. So, sorry, so we're supposed to say 54. So 54y equals 1080. So then we simply divide both sides by 54, which brings y alone, which gives us y equals 20.
Okay.
Wow. You did that really well.
Yes, thank you. And then from there, it's a simple matter of multiplying 3 by 20 to give us 60.
Yep.
Yeah, so I see what you're doing.
And then
You're
so
just
on and so
plugging
forth
them
for the
in.
7 and the 12, which will give us 140 and 240 respectively.
Okay, I like how we have to just find one y to find all of them, 7, 3, and 12.
Right.
Oh yeah, it's taking one brick and then the entire structure crumbles at your feet and the answers are revealed.
Like dominoes.
Exactly like dominoes.
Okay. Well, thank you. That was really well explained, Chris.
You are very welcome.
All right, Willa, I have a question for you.
Yes, ma'am.
Finally.
So, so what's the difference between complementary and supplementary angles?
Okay, so here we're going to be using question 1 from, I believe it's module 2, and it's how do you find the degree of each angle in this figure? So we've got a very complicated figure right there that looks daunting. But we have our table here that gives us the definitions. Complementary angles are the two angles that add up to 90 degrees, while supplementary angles are two angles that add up to 180 degrees. And those are going to be really valid in the explanation for this figure. So we're going to start out finding the angle of the measurement of angle 7. So angle 7 is down here. And interior angles are going to be supplementary, so they're going to equal 180 degrees. So this way, you're going to take 180 minus 65 minus 56 equals 59. So angle 7 is going to be 59 degrees. And so angle 7 right here is angle 1 are corresponding. So those are going to be, they're equal. So angle 1 is 59, angle 7 is 59 because they're going to be equal to each other.
Okay.
So then we're going to take angle 2, which is right here. Angle 2 is the opposite angle of the angle that is 56 degrees right here. So it's with the vertical angle. So with the vertical angle, that means that angle 2 is going to be equal to 56 as well, because the vertical angle is also going to be the same. So because angle 2 is 56, we have angle 3, which is corresponding down here to 65 degrees with the vertical angle, just like angle 2 was. So because it's vertical corresponding, angle 3 is also 65 degrees. So we know that corresponding angles are equal to each other if they have a vertical angle as well. Sorry guys, I had to pause it real quick because my computer's dying.
Okay.
Okay, so now that we've got the major ones out of the way, we can kind of use the complementary vertical angles to figure out the rest of them. So as we said, angle 1 is 59 degrees, angle 2 is 56, angle 3 is 65, angle 4 is 65, angle 5 is 59, angle 6 is 115 degrees, angle 7 is 59 degrees, angle 8 is 121 degrees, angle 9 is 65 degrees, angle 10 is 115 degrees, angle 11 is 121 degrees, and angle 12 is 59 degrees.
It's really just kind of using one to figure out the other and then the other and the other, right?
Exactly. As long as you start with the right one, like angle 7, it kind of falls into place with the other ones.
Yeah.
Sounds
And
good to
I feel
me.
like it's important to note that like 1, 2, and 3 are all supplementary angles because they're all on that straight line. So a straight line's 180.
Exactly.
So you could use that to figure out points 9, 10, and 11, 12, even though you already figured out 11.
Yeah.
But you can still do that.
Yeah, exactly. Okay.
All right, well, actually, I'm going to let Chris ask you this one.
Okay.
I'll be glad to. Miss Willa, I need you to explain what exactly are tetrahedron subset faces.
Okay. So what a tetrahedron is, we're going to actually go back to question 5, module 2. And so how to make a tetrahedron is, it's a triangle pyramid, and it's a polyhedron that's composed of 4 triangle faces, 6 straight edges, and 4 vertical corners. So this little pyramid right here is going to move inside of that square, or that cube. And so the tetrahedron, what makes it a tetrahedron and not just 2 shapes inside of each other, is that they can't share a face. So that shape is going to be independent of the faces of the cube. You know, they're not going to share a face. And so you see where it cuts off, you'll see that that vertices will make your 6th face for it, or your 6th straight edge is going to make your face for it.
Okay.
Alrighty.
So it kind of sounds like this shape is just kind of floating inside of the cube and not actually touching the faces.
Yeah, exactly. They're not gonna share one. That straight edge right there is gonna cut it off and make its fourth face to actually make it a tetrahedron. So they kind of help each other out, but they don't share any kind of faces together.
Right.
Very nice. I liked your explanation, Willow.
Thank you. All right, Chris, this question's for you. What is the doubling system in regards to this question?
That's a good question, Willa. So the doubling system in this particular instance is referring to the fact that each one of the units of measurements that you see below are in some way or another doubled from a number. So you see a jigger is 2 mouthfuls, a pint is 2 cups, a jack is 2 jiggers, a jill is 2 jacks, so on and so forth. So we're going to use these pieces of measurement and the doubling system to answer the following question. So we see it's asking how many mouthfuls are in a jill, how many mouthfuls are in a cup, and how many mouthfuls are in a pint. So here we understand that 2 mouthfuls equals a jill, 4 mouthfuls equals 2 jills, which is a cup, and then 8 mouthfuls equals 4 jills, which equals 2 cups, which equals 1 pint. So you have to notice they're all being doubled in some way. Because if you have one jill and you need another jill to make another cup, then you need double the amount of mouthfuls you originally had, so on and so forth. It's all just doubling itself up in some form or fashion until it gets to the next unit of measurement.
Okay, I like that. Thank you.
You are welcome.
Oh.
Yeah, I really like this the diagram here. It kind of fills it up and shows it to you.
Oh yeah, definitely.
Just like a bucket.
Okay, Willa, I have another question for you.
Ask away.
What is the difference between perimeter and area?
Okay. So we're going to use question 2. I believe it's module 3. And so perimeter is the distance around the outside of a shape, and area is this measures the shape in the space inside a shape. Sorry. So what that's going to do is we have our figures right here, and I'm just going to do figure A to kind of give you what it means. So the formula for perimeter is in a triangle is side plus base. So you're going to use 48.3 right here for this side, plus 68 plus 6 for this side, and then plus 80.9 for this side, because you're not going to use the 41 because that's the space inside. So you're going to use that for area. So if you add all those together, you're going to get 197.8 meters. So for the area, the formula for the triangle is base times height divided by 2. So for triangle A, it's going to be 80.9 meters times 41 meters right here in the middle divided by 2, and that's going to equal 1,658.45 meters squared. And that's how you find the perimeter and area for figure A.
Very nice. Well, very well explained.
Thank you.
Yeah, I can tell now that, like, I was kind of wondering about that 41 meters for a sec.
Yeah, you don't use that in your perimeter, use it in your area formula because it's inside the shape.
Right.
Alrighty.
All right, so Chris, can you define rigid motion for me?
I can and will. So we actually just went over this in our last team teach. So rigid motion is simply a form of motion that a figure can take in which its position or its mainly its position. Its position is changed in some way, whether through being turned or placed in a different spot or reflected in some way. Those are all different forms of rigid motion. However, the size is not changed because that is specifically not rigid motion. So for this problem here, we see that the goal was to try and reflect the figure, and now we have to understand, is the current transformation we see, is that a reflection or is it something else? And if it is something else, what should a reflection actually look like? So this figure right here is actually not a reflection, but a rotation. And you can understand that by looking at a circle as an example. A circle is 360 degrees all the way around. The figure has been rotated 180 degrees of those 360, so half of the circle. And that's how you understand it's a rotation, because it's only been turned a certain amount, whereas a reflection is going to be the original figure staring back at the original figure, the opposite orientation, not vertically, but horizontally.
Okay, that makes a lot of sense. It has to go 360 degrees. It can't stop at like 180 or something.
Right. So the figure you see, the initial figure, is simply going to be staring back at itself during a proper reflection.
Okay. So that would,
Exactly.
yeah, what the correct one should look like.
Yeah, I see it now.
I like that. Makes a lot of sense.
It does.
All right, well, I have another question for you.
Yes, ma'am.
Where does the line of symmetry need to be placed?
All right, so the line of symmetry, we're going to use this as reference of question 2, module 4, or last one. So the line of symmetry is going to be placed where it's going to show the same side. So right here would be the middle for the shape, because the line of symmetry right here, you see these points in particular are